Okay, welcome back. So the next speaker is Alba Grassi of CERN, and she will talk about Painlevé equations, quantum operators, and gauge theory. Please, Alba.
Okay, so hi everyone, and well, thank you very much to the organizer for the invitation to give this talk. And yeah, so what I would like to talk about today, indeed, are various aspects of Painlevé equation, quantum mechanical operator, and in particular their relation with supersymmetric gauge theory. Okay. So what I will be talking about today is mostly based on some work which I've been doing in collaboration with Misha Bursztyn and Pasha Gavrilenko. So this is a relatively recent work. But then I will also discuss some older work which I did a few years ago in collaboration with Giulio Bonelli and Alessandro Tanzi. And okay. So roughly speaking, these are going to be like the three main players in this talk. So on one hand, we have like Painlevé equation and some of its generalization. In particular, we will see the Q-deform Painlevé equation. On the maybe a more physics side, we are going to have a Cyber-Witten, Argyres-Douglas, or maybe more generically topological string theory. And then the third player are going to be quantum curves and more generically quantum mechanical operator and the corresponding spectral theory. And then we will see that there are actually several interesting connections between these three topics. And we can actually constructively exploit this connection to learn something interesting and something new about each of these cards. Okay, and in this talk we will see some example of this. Okay, so more precisely, this is the plan of the talk. So the talk will be structured in two parts. In the first part, we will discuss Painlevé equation, the connection with four-dimensional n equal to theory and Schrodinger operators. Okay. And then in the second part, instead, we will see that there is a particular uplift of this setup to the framework of Q-deform Painlevé equation, topological string on toric Calabi manifold, and a particular type of difference operator which arise when we quantize the mirror curve to this toric geometry. Okay, so this is more or less the plan. And I'm going to start with this part here. Okay. And more precisely, the first step is going to be the connection and relation between Painlevé equation and n equal to four-dimensional theories. Okay. And yeah, so I'm going to start with first the Painlevé equation, and then we will go in this order. So Painlevé equation are second-order nonlinear ODE of this form here, right? So we have a second derivative, which is like a rational function of Q, the first derivative, and then we have the time. And this equation have the particular property that the solution are free from movable critical points. Okay. And in particular, you can actually write down the list of this equation. These people did in the past. And well, if you do that, then you end up with this list here. Okay. So we have, as I was mentioning, a second order equation, right? And then we have Q, we have the first derivative, and so on. And then there are some parameters here, which I colored in blue. So these are some time-independent free parameter in your equation that you can set them to some number or something. Okay. Now, there are several interesting aspect of this equation. For what I would like to do in the following, there is a particular characteristic which is interesting, and this is the fact that we can organize this equation into what we sometimes call the confluence diagram, which is this diagram here. Okay. So what this diagram represents basically is the fact that it exists a particular type of scaling limit which involve, among other things, scaling this blue parameter in a certain way. And when we implement this scaling limit, we can go from the Painlevé 6 equation down to this equation. And the way in which this scaling takes place is precisely encoded in this diagram. Okay. So if we look, for example, at this last line here, okay, so what we mean by this is that there is the 3-2 equation with a free parameter in some sense. We can send this alpha to infinity, the time to 0 in such a way that the product is constant. And when you do that, you go from this one to the Painlevé 3-3 equation, which is this. Okay. And here you don't have any free parameter anymore, so the diagram stops. Now, Painlevé equations have appeared in the past in various contexts in physics. For example, in the context of 2D gravity, in the study of the correlator of the Ising model, and so on. And during the last more or less 10 years, this relation between Painlevé equation and physics has known a new and beautiful development thanks to what sometimes we refer to as the Painlevé gauge correspondence. Okay. Now, when we first hear about this correspondence, there are maybe two straightforward questions that we can ask. The first one is, why should we even expect a relation between these two subjects? Okay. And here, when I say gauge, what I have in mind is like, in particular, like a 4-dimensional cyber-Witten theory and omega vector. But okay, so the first question is, how can Painlevé equation and cyber-Witten theory have anything to say one to the other? And then the second point is, okay, so suppose that we have this connection. Why is this interesting, and what are the new results that we can obtain in this context? And this is what I would like to address now. Okay, so let me start with the first point. And okay, so there are various ways in which we can argue for a connection between these two subjects. One way goes back already to the early 2000s and by the work to the work of Yamada and various collaborators. And one of the observations that they found is basically the fact that this type of confluence diagram that we have in the context of Painlevé equation also appear in physics in the context of 4-dimensional SU2 cyber-Witten theory or Argyres-Douglas theory. Okay. So in this case, we start with cyber-Witten theory with 4 flavors. So we have 4 hypers, and this is what we usually call the NF=4 theory. And then we can implement the decoupling limit, where we basically, here we have like 4 masses. We scale away 1 mass after the other. And if we do that, then we can go to the theory with 3 flavors, 2 flavors, until we end up with the pure SU2 superimmunity. And then we also know, because of Argyres and Douglas, that inside the moduli space of this theory, we have some special point which where we can get the Argyres-Douglas theory. And well, what they notice is that basically these 2 pictures are very similar. Okay, and this is of course obvious if we just look at them, but this is deeper than just a graphical observation. And for example, really the way in which you scale the parameter on the 2 sides is really it's really parallel. If we use an appropriate dictionary, which identify, for example, this free parameter, this blue parameter that I was drawing in the Painlevé equation. So when we do this correspondence, these parameters are identified with masses in the physical context, and the time in the Painlevé side is mapped to the dynamical scale or the exponential of the gauge coupling. Okay. So this is to give us, in some sense, already maybe a feeling that these two subjects are, there is an interesting connection between them. Now, why is this interesting connection? why is this connection interesting, and what are the new results that we can obtain? Now, when we look at this list of equations, there are certainly many questions that we can ask. One question is whether we can construct generic solution of this equation in an explicit form. Okay. There were in the past like some special solution when you fix the parameter in a certain way, or when you choose a particular type of initial condition. But the construction of a generic solution in an explicit form, this was kind of a challenging problem, and this is one of the points where this connection with supersymmetric gauge theory gave, in some sense, a new perspective. And this is what I would like to talk about now. So, for the moment, we can focus on this upper part of the conference diagram. Okay. And what Gamayu, Yorgov, and Lissovi noticed already in 2012 is that basically we can construct a general solution to all these equations in a very explicit form by using a certain function which appear in physics, which is the Nekrasov function in what is called the self-dual phase of the omega diagram. And this is basically the partition function which corresponds to this type of gauge theory here. Okay. Now, the self-dual phase of the omega background, this is the one which, when we think in terms of geometric engineering, make contact with the standard topological string. Okay. And I'm not sure if everyone in the audience is familiar with the Nekrasov function, but that's not going to be very important. I will comment a little bit more on this function and give an example in a moment. Okay. So this is this type of construction. Sometimes we also call it Kiev construction because of the authors. And also, yeah. So let me mention. So this was in 2012. Okay. After that, there have been many interesting developments by several different authors. And also an important point is by now this Kiev construction is actually a theorem. Okay. So people prove this statement also from a mathematical point of view. And the first proofs go back to the 2014. Okay, so let me now maybe illustrate a little bit more precisely this construction in a particular example, which is actually going to be the guiding line example for this talk. And this is, in some sense, the simplest example, which is the one of the Painlevé 3-3 equation. Okay. So this is the corresponding equation. We have a second order equation. So we have two integration constants, which we will denote by sigma and eta. Okay. And on the physics side, this is going to make contact with the four-dimensional n equal to SU2 superunits theory. And then the claim basically of this Kiev construction is that we can obtain a general solution to this equation, which is this, in a very explicit form. Now, here I'm not being very explicit, okay? So what I'm doing is just re-expressing this function Q in terms of this tau function here, okay? And then what the Kiev construction gives us is basically a very explicit expression for this object here, which can be written down in this way here. Okay. So first, notice that we have a sum over integer. Okay, so this is an infinite sum, but you can prove that this is a well-defined convergent sum. And then we have the summand, okay, which is this, where one of the arguments is shifted. And this summand is explicitly computed by this object here. So G here are the Barn G function, okay, and B here, this is another function. This is the Nekrasov function for, in this example, the pure SU2 n equal to superunits in this self-dual phase of the omega. Okay. And yeah, so since I suppose that not everyone in the audience is familiar with this with this function, maybe we can just write down a little bit more concretely what this object is. And we have something like this. So here again, we have like a sum over integer. So we have another infinite sum. But again, you can prove that in this four-dimensional framework, this is actually a well-defined convergence sum. And there is an explicit definition for this CN coefficient in terms of combinatorics of Young diagram, which I'm not gonna give here because it will get a bit too long and too technical, but there is a precise definition of this coefficient. And the first few orders look like this. Okay. So this is basically a Nekrasov function associated to this particular type of theory. Now, when we work in a more gauge theory framework, usually we are used to express Nekrasov function in terms of the epsilon parameter of the omega background, the wave of the scalar in the vector multiplet, which is usually denoted by A, and then the instant-on counting parameter or dynamical scale or exponential of the gauge coupling, which is usually denoted by lambda. Okay, and in the Painlevé context, we repackage this quantity here in sigma and t. Okay, so this is a well-defined object which is given in terms of Barn function and Nekrasov function. You can obtain this object explicitly, which is well-defined and convergent. And when you put this all together, you obtain your solution with the two integration constant in an explicit form. Now, this is the example of the Painlevé 3-3 equation. Okay, but you can actually generalize this construction in a very straightforward way to all these equations here. Okay, and what we do in this context then is we have the same structure. It's just that we have to use Nekrasov function associated to a different type of theory. But this is also something that is new. Okay. So from that point of view, we can think of this Kiev construction as a beautiful example where we have some known result from physics, and in this case, the Nekrasov function, and we can use that to obtain some new results in a more mathematical framework, and in particular in the study of this equation. So from that point of view, this goes in this direction here. Okay. So we exploit what we know from this side to get something here. And then you can ask, okay, so what about the other way around, right? And well, as you can maybe imagine at this level here, this question is particularly interesting because Argyres-Douglas theory are kind of hard to deal with in some sense. But even if we stay at this level here, actually there are some interesting results that you can obtain on this side here by exploiting Painlevé equation. For example, in the case of the Painlevé 3-3 equation, you can exploit some Painlevé knowledge, and in particular the work of Barry, McCoy, and collaborators, to provide an exact resummation of the instant-on expansion which appear in the Nekrasov function. Okay, so as I was showing earlier, this is an expansion around a small value of the time t, or instant-on counting parameters. It's in this four-dimensional framework, this is convergent, but sometimes it's useful to obtain some resummation form. And this in particular when you want to study, for example, the strong coupling or the magnetic frame. Okay, so in that context, you can exploit something here to get some new result on this side. And I'm not going to go into the detail of this construction here. I just wanted to mention that this type of correspondence is really something that we can exploit on the two sides. Okay, and so for complete for completeness, let me also make one more comment. And this is the fact that so far I was really only focusing on this part here. Okay. It is, however, possible to extend this correspondence in this lower part of the confluence diagram, and there are several interesting results that you can obtain in this context as well. But I will not talk about this today. Today we will just focus on this upper part. Okay. But for completeness, let me just mention that we can also go at this level here. Okay, so what we discussed so far can be basically summarized by this picture here. Okay. So what I would like to do now is to, in some sense, introduce a new player into the picture, which are Schrodinger operators. Okay. Now, Schrodinger equations are also the kind of interesting equations which appear often in physics, and for which we have a closed form solution only in few examples. Okay, so having some analytic approach to these operators and to this equation is always very useful. And what I would like to do now is to basically exploit this new knowledge about Painlevé equation and Kiev construction to the study of these operators. Okay. Now, the fact that Painlevé equation and Schrodinger operator are that there is a connection, this also goes back of a while, right? Already in the work of 86 by Novakhinov. And so, for example, what he was not is he was like studying the Painlevé tree equation, okay? And he noticed that the distribution of movable poles in this equation, okay, in the solution to this equation, goes like the distribution of eigenvalue in the mature operator. Okay. And this type of observation was also later studied and extended, for example, by Davide Masoero and also various authors. And in this case, he was studying the distribution of movable poles in some special solution to the Painlevé 1 and 2, and he was connecting that with the distribution of eigenvalue in the cubic or in the Schrodinger equation with cubic or quartic potential. Okay. And one of the questions, in some sense, which motivate partially our work with Misha and Pasha, whether we could maybe understand this relation systematically, right, for the full diagram by using this underlying connection with n=2 theory. And okay, so if you want to look into this problem, the first point is to associate a Schrodinger equation to each of these Painlevé equations, right? And this basically can be done as follows. So we can basically exploit the fact that Painlevé equation arise as admit, let's say, a realization in terms of 2x2 linear system. Okay. So this connection is actually highly non-trivial. Okay. It has to do with the fact that Painlevé equation arise as compatibility condition of monodromy preserving the formation of 2x2 linear system. But I will not go into the detail of this connection. I will just exploit the fact that people in the past studied this connection in quite detail, and today we know very well what are the 2x2 linear systems which correspond to this equation. The second point, which instead is kind of trivial, and we probably all know this, is the fact that once you have a 2x2 linear system, we can associate to this Schrodinger equation. Okay, but the point is that this Schrodinger equation is not yet what we would like. Okay, and in order to maybe make a little bit more manifest what I mean by this, let me maybe first review this part here. Okay. And this is this part here. Okay, so we start with a 2x2 linear system, right? And we can associate to it a set of two equations. And when we combine them, then we obtain directly a second order equation for one of the variables. We can, in addition, perform some change of variable. Okay, and if you do that, then you obtain your second order equation in a Schrodinger form, which is straightforward, where the potential, okay, is expressed in terms of the matrix element of your linear system. Okay. Now the point is the following. So suppose that this matrix element has some zero at some particular value. Okay. So this means that basically when you play here, like we have some additional singularity, right? So when we play this game, we are introducing some singularity which were not part of the original problem, and this is something that we don't want. Okay, when we do this game, we don't want to introduce new singularity. And when you go to the context of Painlevé equation, the 2x2 linear system basically has some freedom in some sense, and it will become clear what I mean in a moment. It has some freedom, and we can exploit this freedom to make sure that this doesn't happen. Okay, and when you do that, you basically have two straightforward consequences. One is that the potential, okay, reduces to a much simpler potential, which I will denote by U of Z, and this is the potential that we are interested in. And the second consequence is that we obtain a vanishing condition for a particular combination of tau function associated to Painlevé equation. And this will be connected in some sense to the quantization condition for the Schrodinger equation with this potential. Okay. And yeah, so let me maybe illustrate this more precisely in our example of the Painlevé 3-3 equation. Okay. So the 2x2 linear system, which correspond to this equation, is given by this matrix here, okay, where Q is a solution to this equation and P is defined in this way. Okay. So if you take this 2x2 matrix, right, and you do this procedure, you end up with a Schrodinger equation whose potential is given by this. Okay. And here I'm also notice that sometimes I'm using x, which is the exponential of z. Okay. And then you see that here you have these points here where you can have some additional singularity in some sense, which are precisely the one which are due to the zero of this matrix. And well, this is something that we don't really want. And in order to avoid the introduction of additional singularity in some sense, we have to sit at some special points, which in this case are q equals 0 or q equal infinity. And in this example, and for what I will be discussing in the following, it doesn't matter on which point you sit. You will get the same conclusion, more or less. Now, remember that these are a solution to the Painlevé 3-3 equation. Okay. So if you remember at the beginning when I was introducing the Kiev construction, I was expressing them in terms of this Kiev tau function. Okay. So from that point of view, sitting at this point means that we are imposing a particular type of constraints, which is this. Okay. And well, when you take the Schrodinger equation with this initial potential, and you sit at this special point where you have this kind of singularity matching condition, then you obtain that this just simply reduces to this potential here, to this equation. Okay. Where this is the like Mathieu, right? Is the Mathieu potential, and you also have the energy, which is explicitly given in terms the Kiev function. And then this is the constraints that I was mentioning. Okay, so this you obtain in a more or less direct way once you decide to be at this point where you don't have these additional similarities. And then, yeah, so we have this operator, and then we can decide to study that in different slices of the modular space. For example, we can decide to study the case where X is real and T is real and positive. Okay. And then in this case, you have a quantum mechanical operator in a confining potential, right? And typically, in this context, we ask for the eigenfunction to be a square integral. Okay. And by basically exploiting the fact that this variable here come from the linear system associated to Painlevé equation, you can show that asking this requirement is exactly equivalent to set these particular constraints on the Painlevé value. Okay. So,
sorry, can I ask a small question?
Sorry, I don't hear you.
Go ahead.
Yeah. What does the second equation mean? Just to be sure.
This?
Yeah. Yes.
I will come back on that in a moment. Okay.
It just seems like, are you sure? Like, if you shift sigma back, your whole function is here. Maybe it's some, I don't know.
No, it's important actually that you have this shift, because you see, if you didn't have this shift, here you will have infinity. So it's really important that these two are shifted. But I think maybe in a moment this will become more clear. But this is basically the condition that we impose when we say
yeah.
that we
You mean T? I was remembering T is a function of sigma. It's like they're not independent. T sigma eta.
In principle, they are independent. T is the time, and sigma and eta are integration constant. Okay. So, and this is the full system. And then when you do this procedure, and you want to make contact with a certain type of Schrodinger equation, then this happens if you impose a particular type of constraints, which is this.
This is a constraint. Yeah, that's what I was asking. What is this equation? Yeah, I was asking you, is it a constraint on T sigma eta? Okay.
Yes, this is a constraint which comes from the fact that we don't want to introduce additional singularity, and in order to ensure that, we have to impose some constraints.
I see. Okay, thank you.
And yeah, and actually this. So in a moment we will. This is going to also be interesting. So, okay, so let me go back. We have this square integrability, which is equivalent, thanks to this connection with Painlevé equation, to imposing these particular constraints. Okay, and therefore, okay, so this is what guarantees square integrability. When you plug this back in, you can get, in some sense, for free. Directly the exact spectrum of modified matter in this form here. Okay. So now these constraints is like if play the role of the quantization condition. Okay, it has a discrete family of solutions which are given by this. And yeah, so this is really an exact result, and this can really be computed explicitly by the Kiev formula, and in particular the self-dual phase of the omega vector. Okay. And this is the example of the Mathieu operator and the Painlevé equation, but you can actually generalize this to the full diagram. And there are various examples which have been worked out explicitly. Okay, so the main, maybe the main punchline of this last part is that we can basically exploit some recent progress in the context of Painlevé equation to obtain some exact result in the theory of Schrodinger operators. Now, let me make one comment, especially for those who are a little bit familiar with the subject. And this is the following. So the type of Schrodinger operator which arise in this context can also be obtained from the quantization of four-dimensional Seider-Witten curve. Okay. So when an operator has an interpretation in terms of four-dimensional gauge theory, there is an alternative way to study the spectral property of this operator, which is by using the self-dual, the Nekrasov-Shotashvili phase of the omega vector. Okay, so this is different from what we were discussing in the previous slide. And during the past, I think more or less 4 or 5 years, the connection between these two phases of the omega background has been studied in quite some details in various situations, and it can be explained and derived by using a particular limit of what are called Nagashima-Yoshioka blow-up relations, which are a particular type of relation that are satisfied by Nekrasov function. And also in this case, you can relate these two approaches using this type of relation. Okay. So in particular, this also means that you can, for example, derive the Nekrasov-Shotashvili type of quantization starting from Kiev formula, and Kiev formula is something that mathematician proved. But okay, so this is really the four-dimensional framework. Okay, so there is a generalization of this framework where things are different. And this is the context of the 5-dimensional, from the point of view of gauge theory, this is 5-dimensional gauge theory. And from the point of view of the operator, this is the framework of differential equation and relativistic integral systems. So when you go to this context, actually the Nekrasov-Shotashvili type of quantization condition has to be supplied by some additional non-perturbative correction, which we computed already a while ago. And an interesting aspect of this Painlevé approach is that you can naturally take into account this type of additional correction. Okay. So this was just to maybe mention an interesting application, but I will not go into the detail of this application. Now, what we discussed so far is basically summarized in this picture here. Okay. So we have Painlevé equation, 4-dimensional n equal to theory and Schrodinger operator, and we saw that we have various connections between these topics, and there are interesting results that we can derive. Now, as I partially anticipated already, there is an interesting generalization to this framework, to the setup of topological string theory to the form Painlevé equation and a certain type of difference operator. Okay. So this is what I would like to discuss in the remaining part of the talk. And again, to get maybe a little bit of feeling of what is going on with this generalization is, I find it at least useful to go back to the picture that I was introducing in the first part of the talk with this confluence diagram. Okay. So what happened when we do this happen? And let me first discuss this part here. Okay. So if we are a little bit familiar with topological string theory, or even if we are not, I mean, basically the point is that this type of 4-dimensional SU2 Seider-Witten theory, this type of gauge theory in 4 dimensions, can be engineered starting from topological string theory on toric Calabi geometry. And depending on which geometry you choose for your string theory, okay, you have string theory on a particular type of target space geometry, and depending on which geometry you pick, you make contact with a different type of 4-dimensional gauge theory in a certain. Now this 2-dimensional like Newton polygon that I'm drawing here these are the one which, according to the work of Gualtieri, Orivath, and so on, these are the one which we can use to represent one of these Calabi geometries. Okay, and we will see an example in a minute. On this side here, instead, mathematicians also understood that this type of Painlevé equation are actually part of a bigger picture, which include what are called the Q-deform Painlevé equation. Okay, so roughly speaking, Q-deform Painlevé equation are difference equation, which have an interesting analog of the Painlevé property, which it's called a singularity and confinement. Okay. So these are difference equations which depend on an additional parameter Q, and they are also such that when you tune Q to 1 in a certain way, you recover the original differential equation. Okay. So this, roughly speaking, is the big picture in some sense. And in the same way in which we have an interesting connection here, also at this level here, we have some interesting results that we can find. And what I will do now is to present some of these interesting results. For example, one thing that we noticed is that basically we can use a freedom determinant of operator which arise in the quantization of the mirror curve to this geometry to compute explicit solution to this Q-deform Painlevé equation. Okay. And as before, let me maybe go a little bit more in detail in one particular example, which is the one of the Q-deform Painlevé 3-3 equation, which I will write down in a moment. And on this side, this will make contact with this geometry, which is the canonical bundle over CP1 times CP1. And we also call it like sometimes local P1 times P1. Now, the quantum mirror curve, which correspond to this geometry, is something that people study a lot in various contexts, and we really know what this operator here is. And in this context, for this geometry, if you use the work of various people, you end up with this operator here. So this is a quantum mechanical operator. So P and X are like momentum and position operator in quantum mechanics. And when you act with this on a function, you end up with a difference equation, which look like this. Now, the point is that the operator which we are interested in and which arise in this construction is not directly the operator that we obtain when we quantize the mirror curve. It's not O, but is the inverse, which we will denote by ρ. But this is not, it's not really an obstacle. We can compute this inverse explicitly. Also, the kernel of this operator can be computed explicitly, and you obtain something like this, okay, where the potential has an explicit expression in terms of the Faddeev quantum derivative, which is something like this. And you can actually also show that this is actually a confining potential. Okay. So this is the kernel that will enter in this particular example. And you can prove that this operator has a discrete spectrum and is also of trace class. Okay. So the trace class property is basically the property which allow us to write down the freedom determinant, which is this object here. Okay. So this is like the product of over all the eigenvalue. And this property here simply means that this is a well-defined product. Okay, so the eigenvalue really decreases very fast. And then the claim is basically that this determinant, okay, for this example, solve the Q-deform Painlevé 3-3 equation, which can be written in this form here. Okay. And of course, this provided we choose an appropriate dictionary, which in this case is this one here. Okay. And also, let me mention that this is a very concrete statement. Okay, we have many tests of this type of statement, but today we do not have a rigorous mathematical proof. Okay, but we do have many explicit checks. Okay, so this is more or less what I was mentioning in the last few slides. Okay, so starting from this geometry, okay, so this Calabi-Yau geometry, we can associate an operator which is usually referred to as quantum mirror curve. We study the inverse of this operator and the Fredholm determinant, and this gives us a particular solution of this Q-deform Painlevé equation. Okay. So what I would like to do in the remaining few minutes is maybe to briefly comment and introduce another subject in this construction, which is topological string theory. Okay. And one way to introduce them is the following. Okay. So the point is that the Fredholm determinant that we were studying before, the Fredholm determinant of this quantum mirror curve. So in this case, we had this expression of the kernel in terms of the Fadeev logarithm. So this object also appear and play an important role in a certain non-perturbative definition of topological string theory on toric Calabi-Yau manifold. In particular, we showed already a while ago that we can extract the genus G free energy of this topological string. So X here is to denote a toric Calabi-Yau manifold. Okay, so we can extract this genus expansion of topological string theory and the corresponding Gromov-Witten or Gopak-Mavafa invariants by studying a particular limit, which is usually referred to as Toft-like limit of the fermionic spectral traces, which are defined from the determinant in this way here. Okay. And you can actually show that these are just a particular combination of the traces of this operator here. Okay. So basically, by taking some particular solution to this equation, which are this determinant, and by considering the corresponding spectral traces, you can extract in a particular Toft-like limit the genus expansion of topological string theory. And well, this is of course like a divergent asymptotic series with zero radius of convergence, but this is really a well-defined object because you can prove that this operator are of trace case. Okay, so from that point of view, this provides the non-perturbative completion. So this, in particular, this solution for this string perturbation series. And okay, so I think I'm almost done. So let me maybe conclude very briefly. So we have, in some sense, there is a deep and also interesting connection between these various subjects, in particular Painlevé equation, Seiberg-Witten theory, and the extension to the omega background, quantum mechanical operator, and also some of their generalization. There are several results which we have obtained thanks to this connection, but I think it's fair to say that there are still many things that we don't fully understand, and while the full picture is in some sense still under construction, and there are also many interesting applications that it would be nice to exploit a little bit. And with this, I think I'm done. So thank you very much, and sorry for going a bit over time.
Thank you very much, Alba, for this nice talk. Questions? I suggest you just unmute yourself or raise hands. I see a raised hand of Cyril. Please, Cyril.
Hi, but thanks for the nice talk. My question is, let's say in the 4D case, is there an understanding of why the Painlevé equation arise? I mean, so you took some, if I remember correctly, you took some ratio of essentially the Nekrasov-Partian function that then solved the Painlevé equation. But is there a reason why? Is it some kind of word identity, or is it because of AGT or something like that? Or?
Yeah, okay, so you can motivate that in various ways. AGT, yes, Nekrasov function is related to by AGT is 2D conformal field theory. So for you, it's more natural to think that the conformal field, and this is what people did in the old days, right? They were using conformal field theory to study Painlevé equations. So from that point of view, yes, you can use AGT to relate Nekrasov function to conformal field theory, if this is more natural. But also you can understand, so here I was mentioning the work of Yamada and so on, but you can also understand this by using the fact that Painlevé equation arise from the point of view of isomonodromic deformation. Okay, and there you really have this picture with a sphere with puncture, which also arise in the Gaiotto description in some sense. So this is maybe another way to see this connection.
Right. I see another raised hand. Yifan.
Hi, Alba. Thanks for a nice talk. I just have a quick question. Is there any understanding of the higher rank generalization of the Painlevé equations and
Yes.
the relation to the Schrodinger problem?
So not really. So when you it depends what you. So if you think higher rank gauge theory, okay, right. This corresponds from the point of view, if you think of Painlevé equation as isomonodromic deformation of
higher rank, yes.
Yes, these are higher rank system, and yeah, there is an understanding. There are several work which were done, or this is already. It's true. This story is also that I didn't mention in my talk this fact at all. But yeah, there is an understanding on this, and this also goes back. Like, I'm not sure if that was the first paper, but I remember, for example, a paper by Pasha Gavrilenko in 2015. Where he was discussing already this story, and after that, this has been also extended.
So potentially there is a much richer, like this kind of diagram, contingent diagram for these higher rank cases.
It is actually much richer. It's just if I add too many things, then people, I won't be able to.
I see.
To get to them. But yeah, this is also an interesting aspect that has been explored, and still. But I should say that in the higher rank, in the rank 2, there are many things that have been worked out in full detail. In higher rank, there are less cases that have been fully worked out. Also because there are much more theories, right?
Right. And also just to get the intuition correct. So the relation between 4D gauge theories, even just the rank 1 case. Or 4D, 4D theories with rank 1 case with Painlevé, it really is through the class S construction, right? Because there are other rank 1 theories, like rank 2-3 theories. I guess it's not obvious what kind of a Painlevé equation it would be associated to.
Well, it depends. What kind of So
there are 40 into 3 theories, which are non-Lagrangian, doesn't have a gauge theory description. Also does not have no class S construction.
It doesn't have a class S construction. Then I wouldn't really know.
But you could still define its Nekrasov operating function, even though we don't know how to compute them. So you could conjecture there's some equation that's satisfied by this physical objects.
Yes, probably yes. It's just right now I wouldn't know which equation that is, but maybe you can find it, and probably you can.
Yeah. Thank you.
More questions? Yes.
Yeah, following up on that for the connection to classes, is it so you fix a Gaiotto curve with fixed poles and so on, and that defines a linear system? Some isomonodromic problem for you?
Yes.
Okay. And so in principle, is it clear why there is this particular, you have this relatively small set of Painlevé equation? Why? What happens if you have more general curve even of type A1, right? Higher genus with.
Yes, in the case of higher, so if you in the case of higher genus, then you will have quiver theories, right? Non-linear quiver theory in higher genus, and you can look at the corresponding isomonodromic, like the 2x2 linear system corresponding to that as well. This I don't think has been studied very much, but also in the case of quivers and so on, you are supposed to have an equivalence in this.
Thanks.
Okay, I see a question by Julia, please.
Thank you for the nice talk. There are several kinds of discrete Painlevé. There is multiplicative one, additive one, and elliptic. So do you have any view for the generalization to the two more cases?
Yes, so what I was discussing was multiplicative, right?
Yes.
So elliptic, yes, that should correspond to, from the point of view of gauge theory, to 6D. 6D. For additive, additive discrete, I actually don't know. I don't know, maybe there is, but I just don't know.
Thank you.
So I might try to answer. Probably it was guessed by Bursztyn that they should be solved by the same 4D Nekrasov partition functions, but considered as functions of thetas or of masses, because different Painlevé equations live in the same family with the differential ones.
Okay, but
like one is symmetry of another in this Sakai classification.
Yeah, yes, yeah, that's true. Yeah, so yeah, you can this additive difference are related to the standard differential, but okay, I didn't know. So you can basically extend the Kiev construction in a straightforward way, and these are also given in terms of 4D theories.
Probably yes. I think nobody checked this explicitly, but maybe it should work like this.
Okay. Yeah. Thanks.
Okay, I see still one question by Hossein, please.
Hello. Hi. Can you hear me?
Yes. Yes.
Yeah. Thank you for the talk. I was just wondering. Is there any relation between Painlevé equation and equations and topological recursion
Yes.
in general?
Yeah, of course. Yes. There is. You can. So there are various ways in which I can answer this question. One way is to say that if I know Kiev construction, right, this is straightforward, because we know that if you expand the Nekrasov function in the epsilon expansion, you obtain a quantity, like the epsilon expansion of Nekrasov function. It's known to satisfy the topological recursion. Right? So this is one way to answer that question. So knowing this Kiev construction is clear that a particular series expansion of this object is captured by topological recursion. You can also argue about that without using Kiev construction, and I think this is, for example, what Koei Iwaki has been working on. So even without using Kiev construction, you can connect the expansion of Painlevé equation to topological recursion. But
So
let me maybe just say one thing is that what you get with topological recursion is going to be necessarily divergent. Okay, while this Kiev construction, okay, the way in which you write Nekrasov function, these are convergent quantities. If you try to work with topological recursion, you necessarily get divergent quantities. Yeah.
I see. Okay. And is there any reason behind this discrepancy?
No, it's just because if you think in terms of Nekrasov function, right? I was writing this in this way. Okay. So when I think in terms of if I want to make contact with topological recursion, I usually do that. Okay. Now this is well-defined and convergent, but you can do a series expansion. Let me think. I think it's like this. So maybe there is the two. It's not. Maybe it's one or something like this. And then you usually let me take the log. Okay, not directly this. And then this is going to be something like this. Okay. So in some sense, you are doing an expansion of Nekrasov function. And we know that sometimes when we have well-defined function and we do perturbation theory, then we end up with some divergent function. And this is basically what is happening here. And the topological recursion basically computes for you this quantity here, which you can then resum into a well-defined function, which is Nekrasov function.
I see. Thanks.
Can I just ask what the references are for that?
Sorry?
Just references for what you've written here.
This why Nekrasov function has this type of expansion.
Right, yeah, and the connection to TR.
Okay, so I can give you, there are certainly better references than the one I'm given, okay? But so one point is that basically topological recursion, okay, in this context here is like holomorphic anomaly. And this is explained in a paper by Orantin, Einard, and Marigno. And the fact that the Nekrasov function, when you take this, when you play this game, goes the fact that this series expansion is controlled by the holomorphic anomaly. This goes back to the work of Albert Clem, Minshin Wan, and Amir Kashanipour. Sorry for the order, it's not alphabetical, but yeah. I don't remember the name, the number of the paper. This is probably 0906, for example. This one I don't remember. Yeah. Orantin, yes, I think these three, Einard and Marigno, have a few papers together, so it's going to be hard. And if you want to study without using this technology, this is what Koei Iwaki did. I don't know.
Yeah, okay, thank you.
Okay, thank you for the nice talk and for the nice discussion. Are there more questions? Okay, if not, let's thank the speaker again. And I think there is a break now of about 1.5 hours. And I assume that the Zoom will still be open if you want to discuss. Okay, thank you.
Thank you.
Bye.